Hello, welcome to the second video lecture for Chapter 14. In this one here, we will look at the ideal gas law. I have my wonderful guest lecture series continuing throughout all the wonderful chemistry teachers here at Brookline High School. And without further ado, here's Elizabeth Leslie.
Thank you. So I'm going to tell you about the ideal gas law, which is one of my personal favorites, often referred to as PIVNR for the letters, PV equals nRT. So the most important thing about the ideal gas law is R here. This is referred to as the ideal gas law constant. Now, the constant that you all will be using in your class is R equals 8.31, and your units are joules over moles Kelvin. Realize, in chemistry classes, they often use R equals 0.0821, which is liters times atmospheres over moles times Kelvin. So the different units you use give you different constants, which determines what units your variables have to be in. So as long as you're using this R, 8.31, then P, your pressure must always be in a unit called pascals. V, your volume must always be in meters cubed, which is equal to a liter. N is always the number of moles, pretty much no matter which one you use. And your temperature is also almost always in Kelvin. Hopefully you remember if you have Celsius, you just add 273 to get it into Kelvin. From there, it's pretty easy. You can rearrange to solve for absolutely any variable that you want to. You're good to go. So now, I'm going to take a second and erase and show you how you can relate the ideal gas law into Boyle's, Charles, and all these different. Okay, we're back. Because the ideal gas law has R and it's a constant, if you rearrange it to solve for R equals PV over NT. Now since R is always the same, I can set any set of PV over NT equal to itself. Now as usual, we try to keep them straight, so we'll put a bunch of little ones and twos. Now here's the thing. If you look at Boyle's law, he simply says P1 V1 equals P2 V2. There's some other guy's law that says V1 over T1 equals V2 over T2. You can use all four variables or any combination of two. So the PV, VT, PT, PN, you get the point. All right, so if a problem, you're doing a problem, it says pressure 1 is this, volume 1 is this, pressure 2 is this, what's volume 2? If it does not talk about moles or temperature in that example, you just ignore them and it simplifies to P1 V1 equals P2 V2. But you can do that for any combination of variables. So if you know this one equation, the ideal gas law, rearrange it, set it equal to itself. Stuff that's not mentioned in the problem or stays constant, you ignore. You can use this for anything and everything. That is why the ideal gas law is my all-time favorite.
Jackpot! Thank you. Done.
Good?
So I want to thank Elizabeth for coming in here and doing that. I just want to really wrap up and touch on a couple things. First off, the ideal gas law it's really just a model of what a low-density gas, what we can predict that it will do. There's no such thing as an ideal gas, but we can come pretty close to predicting and following along the changes in pressure and temperature as we go through for volume. But there really is no such thing as an ideal gas. We use a lot of things that we say they're ideal gases, but it doesn't exist anything like that in nature. Here's what Miss Leslie was kind of touching on when she was looking at solving the equations. We've already used the Boyle's law, saying that temperature and number of moles are constant. When we did the syringe lab, when in fact the temperature went up, increased some amount, but we were able to solve the lab and do that activity within those restraints. The temperature probably did not increase enough to the measurable point that we were able to follow along there. But just kind of some ideas here that she kind of touched on, just a little bit more review, wrapping up and showing you the equations again. when you make a graph for the pressure and volume of some gas at the same temperature, on a pressure on the y-axis and volume on the x, you get what are called isotherms. And these here are, if we follow the line, that means just the same temperature. And you can have lines on the graph, and as they'll show here, and this will come back into play when we're looking at thermodynamics in a little bit when we return from break. But the temperature is constant along these lines, and as the pressure and volume changes. All right, questions for tonight. Why do soda bubbles, and those are the little bubbles that are in soda, why do they grow larger as they rise or ascend within a glass of soda? So think about the little bubbles. Why do they move up? And what I want you to do is also, in answering this question, think about the pressure as the soda bubbles move up the thing. There's also a little thing in the book that you can go through and read to make sure you fully understand this question. And then finally, what volume is occupied by 1 mole of an ideal gas at a pressure of 1 atmosphere and a temperature of 0 degrees Celsius? The hint for this one is how many pascals are in 1 atmosphere and what is the temperature in Kelvin. Thank you very much. Hope you're enjoying the guest lectures, and have a good night.